Okay. Okay, so here's kind of a first look at your next homework set. So in the first problem, I have a family of sets, and it could be a very large family or very small, contained in some universal set U. Show that the following statements are true. When you take the complement of a big union of these sets, it's the same thing as the intersection of the complements of the set. And we're going to talk about what all this stuff means in a moment. When you take the complement of a big intersection of these sets, it's the union of the complement. So it's sort of taking the complement of a union turns it into an intersection of complements. Taking a complement of the intersection turns it into a union of complements. Kind of a little role reversal there. And in part C, what happens if this index set is empty? What happens to the results there? In number 2, we define the symmetric difference of set A and B to be A delta B is A minus B, so that's the step in A not in B, union B minus A, right? So I can draw a picture of this, although this does not constitute a proof of anything. So if this is A and this is B, then A minus B is this, and B minus A is this. And when you put them together in union, this is called the symmetric difference. How many of you have seen the symmetric difference before? If you're in computer science, some kinds of engineering, you might have seen this before. Basically, this operation is sort of like addition, and intersection is sort of like multiplication in a certain sense. Number A, show that the symmetric difference is the same thing as the union of A and B, and then take away the intersection of A and B. 3, show the symmetric difference of A and A is 0. Show the symmetric difference of A and the empty set is A. And finally, show the distributive property. When you intersect the symmetric difference of B and C, it's the symmetric difference of A intersect B, A intersect C. So this is basically like multiplication distributes over addition. That's essentially it. And not finally. Let A and B be sets. Recall that if X is a set, then PX denotes its power set of all subsets of it. Show that the power set of the intersection of two sets is the power set of the first set intersect the power set of the second set. So this behaves nicely. Power set of an intersection is the intersection of the power sets. Show that the power set of A union the power set of B is contained in the power set of A union B. So it's a little bit different here. And C, find a general condition based on comparing the sets A and B such that you can actually get equality. So find me a condition comparing A and B that tells me when you can have equal signs in part B. And finally, this one's a fun one. It's a brain tickle. I want you to think about this. Given what we know about sets, is there a set of all sets? So to think about this problem, let's assume, just for giggles, that there is out there in the universe somewhere a set of all sets. And think about this set here. The set Y of all sets that do not contain itself, that doesn't contain itself as an element. Remember how we talked about the possibility of a set containing itself as an element, right? The set of abstract thoughts being an abstract thought. Think about this and see if you can figure out if there's a set of all sets or not. That one's kind of a fun brain teaser. Any questions on that? Okay. So let's get back to where we were. Should find here. The last time, let's see, we were talking about, we talked about this long list of these sets, these operations on sets. Let me kind of list these for you really quickly so that we can talk about some of them. So we have this just awful list of 17 things here. What do we have? Well, we have that A is contained in A intersection or A union B. Two, A contains A intersection B. A intersect the empty set is empty. Four, A union the empty set is all of A. We had A intersection with itself is A. We had A union itself is A. We had the order doesn't matter. That is, in either direction, that is A union B, is B union A. Number 9. Number 9. Go. A, take away the empty set is A. Empty set, take away any other set is empty. A union, B union C is A union B, union C. A intersect, B intersect C is A intersect B, intersect C. We have the distributive laws. So I want you all to think about what you think are the toughest ones. We'll prove a couple of things. Um, 15. A is contained in B. If and only if A union B. 16. A is contained in B. If and only if A intersect B equals A. And finally, if A is inside B, then we're good to go. You're good to go. Yeah. All right. A intersects C, B is contained in B intersects C, and A union B is contained in A union C, is contained in B union C. Okay. Some of these might appear obvious to you. Somebody, I'm taking a few requests. What do you want me to prove? What's that? Great. A intersect the empty set is the empty set. Okay, so all right, let's be careful, right? Let's do 3. How do you show that 2 sets are equal? What do we do? What's our strategy?
Each one of the steps that would be up here.
That's exactly right. So you want to show that this lives inside this and this lives inside this. One of these is easy, and I'll do this easier. This is true because the empty set is a subset of all sets. Right? What about the other? Let X be in A intersect the empty set. What does it mean to live in the intersection of any two sets? It has to live in both of them, right? So X is in A and X is in the empty set. How many elements live in the empty set? There aren't any. It's a contradiction. So there doesn't exist X such that X is in A intersect. So A intersect the empty set. In fact, we probably could have just done that direction and covered it all. Any questions? Yes.
So the set is just like denoted as A, but is any set intersecting with the empty set always going to equal the empty set?
I'm sorry, run that by me again.
I was just asking if any set that intersects with the empty set, is that always going to equal the empty set?
That's right, because anything that lives in, take any set you want, you intersect it with the empty set. To live in there, you have to live in both the original set and the empty set, but nothing lives in the empty set. Okay, other requests. Okay, that's a good one. Let's do 16. Let's do 16 and let's do let's do 13. This one is an if and only if, right? So I've got to go in two directions. A is contained. I want to show that A intersect B is equal to A. Right. Okay, so I'm gonna go through this carefully. I'm gonna do two inequalities. So let X be in A intersect B. This implies X in A and X in B. That's what it means to live there. Right? So, in particular, X is in A. So if you live here, you have to live here. So what I've shown here is A intersect B, it's contained. Right? Now, let X be in A. And we want to show that it's contained in A intersect B. But as X is in A and A is contained in B, then X is in B as well. Everybody agree? So my conclusion. So X is in A and X B. So X is in A intersect B. So now we've shown that A intersect, or I'm sorry, A is contained in A intersect B. So if A is contained in B, we've shown that A and A intersect B is the same. Agree? Now we got to do it the other way. This one might be easier. I think there might be less to show. Now suppose, and let me write down what we're showing. We need to show I think this is. So let X be an A. And we need to show that this A also lives in B, right? Let X be an A, but A is equal to A intersect B by our assumption. So X is in A and X is in B. So X is in B. Therefore, A is contained in B. So that way we go a little bit easier. Okay. Yes.
So how, X being an element of A, like, can you prove that, or X being an element of the intersection of A, and can you prove that A is consistent? Oh,
So
cause isn't, like, if A is a set, like, how is it a set into the intersection?
well, so it depends on, are you talking about when we prove this?
Yes.
Or you're not talking about this?
No,
Okay, so. Right. So we're under the assumption here that A is sitting inside of B.
oh.
Right, that's our assumption, that's our governing assumption. Does that clear it up for you?
Yes.
Okay. Any other questions? Let's do 16. I'm sorry, let's do 30. So 13, we want to show two sets are equal. Need to show that A intersect B union C is equal to A intersect B union A intersect C. So this is a double containment thing, right? Show this. Let's go through the details here. And let's take this apart. What does this literally mean? X is in A intersect B union C. This means X has to live here and it has to live here. Agree? Write that down. Oh, and let me point out something about writing proofs. Does anybody want to criticize what I just wrote down here? So X lives, so I look at this, X is in A, intersect B, union C. So I say, okay, X is in A and X is in B or X is in C. Anybody want to criticize this? I think I would criticize this. Yes,
It's hard to tell exactly what you mean. If you're not
it's
verifying.
not clear what I mean. Do I mean that X is in A and X is in B, or maybe X is in C as well? Right? Or does it mean that X is in A and X is in B or C? This is what I mean. Don't be afraid to use those, right? This means X lives here and it lives here or here, right? So in particular, no matter how you slice it, X always has to live in A, right? So, so from this, well, anybody give me a next step here. So I know that X lives in A and X lives in B or X lives in C. This is me.
It means that X is in A and X in B, or X is in A and X is in C. Okay.
So X is in A and it is also in either B or C. So no matter how you cut this cake, X lives in A, but it's also in either B or C. Right. Hence, X is in both A and B, or X is in A or C. Because we've established that X has to live in one of these two places, and in either case, it has to live in A. So it's either living in B and A, or it's living in C and A. Everybody agree with that? And what does this mean? X is in A intersect B, or X is in A intersect C. And there we go. We've logically gone through the sequence of steps. If X lives in A and B or C, then X lives in A and B, or X lives in A and C. Do I agree with that? We gotta show the other containment. So let's do this. So let's show this. So suppose X is in A intersect B and or A intersects. What does this mean? Again, you have to live in one of these two places. Right? So what can we conclude? Where does X have to live? Sure. Yes. Right? Because you either live in A and B or you live in A and C. And no matter how you cut that, you gotta live in A, right? What about the other place? Well, you gotta live in one of these two places. X is in B or X is in C. Has to live in one of those two. Therefore, by the way, this little kind of three pyramid dot, that's a shorthand for therefore. X must be in B or C. So we have established X is in A, got that? And X is in B or C. Any questions on that? Any questions? Okay, here are some more problem sets. And then we're going to get into more sophisticated intersections, I guess. See if y'all can help me out as we go along here. We have some universe. Theorem 226. Let U be our universe. It's our universal set that all these sets in the theorem are contained in, and A and B subsets of this universe. Then, number one, what happens, do you suppose, if you take some set A, look at its complement in the universe, and then look at the complement of that? It should be, right, it should be kind of a role reversal thing. Take A, everything not in A, everything not in A, right? It should be A. We want to prove that. A union, its complement, what should that be? It should be the universe. Everything in the universe is either an A or it's not an A. You probably know what's coming next. What happens when you intersect something with its complement? This should be the empty set. Very good. Okay. 4. This is sometimes quite useful. This is set minus. This is all the crap that's in A, but not in B. Can you put that in terms of complements and maybe intersections?
Could be intersection component of it.
Oh, you're close. You want everything to be in A, for sure. And you don't want it to be in B.
Intersection with B's complement.
Good. I'd say sometimes it's actually useful to do that, to write it that way, because you can turn that in terms of set minus in terms of complements, intersections. 5. This one's kind of a fun one. Suppose A is contained in B. So here's a picture, not a proof, just to help me out. Suppose A is contained in B. What are you supposed to the relationship between the complements of those two sets are? How do you think the complement of A and the complement interact?
Complement of B's complement.
Contained in. It's a role reversal, right? Because in this situation, the complement of B, I'll do it kind of in white here. That's the complement of B, and the complement of A includes everything except that little circle, right? So the complement of A is the big one in this case. 6. A union B complement. Anybody want to guess at this? This is actually very famous in the set here. It's got lots of applications. Want to take a stab at that? Complement does, yes.
The A complement or B complement?
Oh, you're close. Actually, the fun thing about this is it flips this upside down. It's the intersection of this. Maybe we should prove that one, huh? 7. A intersect B complement is A complement union B complement. And 8. 8. A intersect B. If and only if A is contained in B complement. By the way, there's nothing special about A is, this also means, I didn't write it down, this also means that B is contained in A complement as well, right? But I only need one of them to do that. So let's do this one. Yeah, so let's do 6 and 7. This will illustrate a good point. And we'll do 1 as well. Okay, 2 sets. I want to show that they're the same. Let's show this first. And let me recall, because this might be useful. Oh, that this is what the complement is. It's everything in the universe that's not in the set. So let's let X be an A complement. Complement. Okay, you know what? This is really confusing for my, small brain parents, the cousins and all. So let's write down what this is. What does it mean for X to live in the complement of the complement? Right. Well, let's see. This is the set of X in the universe. In fact, I think I could do this without even. This is X in the universe, so X is not in a complement. Right?
If I agree.
Or
X is in the universe, but it's not in A complement.
But since X is not in a complement, and a complement is a set of X in the universe such that X a complement, right? X not in A. Then X is in A. A complement is a set of everything in the universe that's not a complement. So if X is not in a complement, which is what it means to live here, then it's in the set of everything in the universe that's not in A, right? But X is not in there, so X is in there. Everybody follow that? Okay. Now suppose X is in A. then X is not in a complement. Right? But if X is not in a complement, then by definition, X is in a complement. And so we've done both. Right, okay with it? I will do 6 and 7. Any questions on this? Okay, let's do 6. Okay, 6. What's this mean? So X is not in A union B. So what does it take for you to live in a union, right? To live in the United States, to be a United States citizen, you only have to live in one of the states, right? So to speak. So what does it mean for X to not live in this union? Okay. No, that's wrong. If X lived in either one of those, it would be in union. So X can't live in A and it can't live in B. Agreed? So doesn't this mean this is what it means to live in A complement? This is what it means to live in B complement, and you have to live in both of them. Any questions on that? Everybody see that? Okay, how about the other? So what we've shown is oops. Okay, let's do the other. Now suppose X is in A complement. This is almost kind of a reversal of what we did before. We want to show that it lives in the complement of the union. Everybody agree with that assessment of the situation at hand? So X is not in A and X is not in B either. But X doesn't live in either of these two. So X cannot be in A union B. Because it doesn't live in either of these states, so it can't be a citizen of A union B. Hence, X must live in its complement. Therefore, A complement intersect B complement is contained in A union B complement. And so we've got both containments. And we've established that. I must be bored today, right? Because this is gonna be very much like the other. But I did say I want to prove it. So how would I go about proving this? I could go about this the same way. See me skin a little bit? Yeah. I'll give you a hint. I have armed myself. I have proven these two things. Now, here's a little mathematics. This is one of the cool things about it. I want to show this, right? This is my goal. Agree? Here's what I know. I know that because I just proved it. Right? Let's take the complement of both sides. Everybody okay so far? Okay. So what's another name or another way to look at this?
A, B.
Okay. So this right here is A union B complement complement. Right. How about right, right. Um, uh, so if I take the complement of this, let's see, I guess I'm sorry. Let's start this one over again. Let's look at let's start right here. Let's look at and I'll give you a hint. Somehow I want to use what I previously knew up here, something about intersections, complements, and so forth. Any ideas? Any ideas how I can use what we've done here to get number 7? Well, you could, yeah, you probably do this, but let me do something like that might seem sort of a little bit silly first. This is A complement intersect B complement. Right. All I've done is I've replaced A with A complement, and I've replaced B with B complement. Everybody agree? So, what does that help me do here?
Six.
Okay. Now, what I want to do is apply 6 with and replace a complement we'll replace, A with, a complement. That's essentially what we're doing. So what does this say? A and B with complement. So here, in number 6, what it says is that if I have something complement intersect something complement, well, that's AC and BC here, right? Replace A with AC, I've got intersection B with BC. This should be something complementary. Right. And this should be what? AC. Everybody okay with that? Right. This is just using this with A replaced by A complement, B replaced by B complement. So that should be A complement, union B complement, complement. Right. So what can we do now? Well, now we can apply 6 again. Right? And this says Bill Union Fred complement is the complement. Okay, so I have created a mistake here. Oh yeah, this is the complement of this. Right, so what I've done is I've replaced this with I'm afraid we've kind of run out of time here. So I'll give you extra credit if you can finish this. I'll finish this on Monday. But so I apologize for this, but so here's some extra credit, and you've got till Monday because I'm going to fix this on Monday. Use 1 and 6 to get 7. Extra credit back. But you gotta be, it's gotta be in by Monday. Before class. Okay, any questions? By the by, the math club meets today. And we're gonna talk about storm surge.